Okay, LeetCode 36. Could this board lead to a valid solution for Sudoku? Doesn't mean that you can actually solve it, it just means there aren't any duplicates in rows, columns, and 3x3 neighborhoods. Here is a Sudoku board. This is the example we're given, and we are going to check it for rows, and we're going to check it along the columns, and then we're going to also check the 3x3 neighborhoods. So we need to isolate those rows, columns, neighborhoods, and then we need to check for each one of those if they have duplicate digits. And let's start with the difficult part, which is the 3x3 neighborhoods. Okay, LeetCode 36. Could this Sudoku board possibly be valid when fully filled? Just means that there aren't any duplicate digits in the rows, columns, and 3x3 neighborhoods. Here is our Sudoku board example, and to create the rows and the columns separately is really simple. We just do a concatenation reduction, trailing axis, that gives us the rows, and if we put a bar on this one, that gives us a vertical reduction, and that gives us the columns. The difficult part is getting the 3x3 neighborhoods out. The way we could do this is to look at the board as a 3x3 collection of 3x3 character boards. That is, all in total, we've got ourselves a four-dimensional array of shape 3, 3, 3, 3. So we reshape the board into that row, Greek row, like the letter R for reshape. And it's a little bit difficult to read because there's so much data here, but we can see the layers here. So this is our layer, and here's another layer, and here's another layer. So this forms a cube, and then we can see there's a double line spacing here for the next cube. So we've got ourselves a hypercube four-dimensional array. Now the problem with this is the ordering of the elements. If you put this next to the board, then we can see here that these 3x3 blocks were made from the Revel order, the order of appearance, rows contiguous like this. And that's not right, because we want after the 5, 3 dot, we want the 6 dot dot, which is down here. So overall, we begin with this neighborhood up here with the 5, and then down here, after the double space, we got the 8. So the first dimension is quite alright. And the last dimension, where we have adjacent 5, 3 dot, and then 6 dot dot, that's also correct. The problem is that dimensions 2 and 3 have been swapped. So we can fix this by using dyadic transpose, which is really reordering of axes. We want the first axis to become the first axis, and then we want the fourth axis to become the fourth axis, that stays. We just want the second axis to go to position 3, and the third axis to go to position 2. And now, if we go and look at this, we can see that we've got this neighborhood here, and it looks exactly like the neighborhood over here. This is what we want. Next step then would be to isolate them so we can work on them individually. We do that with the enclose function, and we're enclosing two axes, two trailing axes. That's called enclose rank 2. So this operator specifies for that we're going to enclose not the entire array, but we're going to traverse it and find subarrays with 2 dimensions, and we're going to enclose that. So that's going to be these 3x3 neighborhoods. Each one of them gets enclosed, and now we've got a 3 by 3 array of 3 by 3 neighborhoods. So we can see that matches with our board. Now, we don't actually need these boards to be 3 by 3 arrays. So instead of enclosing them, we could also just ravel them individually. So now we've got a 3 by 3 by 9 array, and each row here corresponds to a neighborhood because we just want to check if there are any duplicates. We don't care about the actual shape of the neighborhood itself. And now we can split this into individual rows. So we've got a 3 by 3 array of 9-element character vectors, and then we can ravel that to get ourselves a list of 9 such flat strings if you want. So this is the first step. Let's replace the board here with omega, which is the rightmost character in the Greek alphabet. That refers to the right argument. It's the argument on the right. Now board over here is the argument, and we get just this collection. So this takes care of neighborhoods. If we then create a fork, which is we have a function on the right that gets applied to the argument. We have a function on the left, which is our vertical concatenation, which gives us all the columns. And then we have a function in the middle, which combines the results from these two functions, also with concatenation, and that should give us a 18-element list of first columns and then 3 by 3 neighborhoods. We can try that, and we can check that it has 18 elements with a tally mark, and then we can further concatenate the rows. That should give us 27. So now we've got the 27 character vectors that need to be checked. So we've isolated the data that we need to look at, and then we apply a function for the actual checking. And the function is going to be a little lambda, where we take the neighborhood or column row contents and do the intersection with a collection of digits. So this is a system constant that just contains the digits from 0 to 9. And we do that on each one. And that gives us these. Now we've removed the dots that are there. We could also just remove the dot character, but this allows us any filler character that's there. And then we can apply the nubsieve or indicate first. And this is a function that returns a boolean for every element, whether or not it's the first time we see that element. So in this case, it's going to be all 1. And then we can ask, are all these ones, is it true that all the elements are unique? And then we get these 27 ones. And finally we ask, is it all true that all the rows and columns and 3 by 3 neighborhoods are consist entirely of unique digits when ignoring everything but the digits? And that says that it is. Another example we had, let's give this a name for now, is valid Sudoku. Right there. And then we can look at the board, and we had an example where the top left number was replaced with an 8, which would be clashing with this 8 down here, so we can see if this works. One way we can do that is say the first row, first column gets assigned the character 8. Now we can say, is it a valid Sudoku? The board, and it says it's not.